In this video, I'm going to be going over the dynamic time warping algorithm, which is used for finding the optimal alignment between two sequences of data. And it's usually thought of as a time series of data, but it can be any type of sequence. And along with the alignment comes a cost or a distance between the two sequences. And this has applications in various forms of pattern recognition, things like speech recognition. And the distance between the sequences is often used as the distance metric in clustering algorithms. And so it has a lot of important uses. I think a good place to start would be with two sequences that have a distance of 0 between them. And I can use this as an example to show what I mean by alignment. And so some things to note here are that this top sequence has 8 elements and the bottom has 10 elements, and that's kind of a key idea of the time warping aspect of this, which is that you can essentially stretch and skew sequences by repeating parts of it without paying too much of a price when it comes to evaluating the distance between them. And for alignment, what's meant is that each element in a sequence pairs with only one element in the other sequence, and you end up with something like this, where you can imagine each edge having a cost associated with it. And in this example, the distance between these two sequences is 0 because you can always match an element with the same element above it and below it. And also important for alignment is the fact that these edges never cross. You can't reach back once you've consumed input, is kind of the way I think about it. And also for alignment, something that's important is to note that the last elements of both sequences have to be paired, and the first elements have to be paired. You can't take this first A and then reach into the middle of the sequence. So that's the simplest example. It gets a bit tougher when we have to consider when the elements don't just match perfectly. And so here you can see that we're going to be forced to pair the F and G, and so we're going to need to have some type of distance function for comparing them. And so I just want to point out that these elements, they don't have to be just numbers. They can be vectors or anything that you can define a distance function for. Later on in this video, I'll be doing an example with just integers, and for the distance function, it'll just be the absolute difference between those two numbers. And so for finding these actual alignments, you need to pick which element to pair with. In order to do that, we're going to need to use a dynamic programming approach. To illustrate the dynamic programming approach, I've drawn some dots here. So this represents one sequence and this represents another. And we're basically going to ask ourselves what happens when we introduce a new element here at the index I, assuming that we already have the solutions, the optimal alignment and cost between these two subsequences here. So we're basically just adding on a single element, and we want to see how we can reuse the solutions that we already have. And so one possibility is that when we add in this new edge, because remember the ends have to pair up, that we just use the optimal solution from the previous elements like this, using all these elements. So that'd be I minus 1 and j. And another possibility is that we're using I minus 1 and j minus 1. So here that's kind of like using the solution to this subproblem that I've kind of drawn out in orange. And it's kind of like this element here in the pink solution, it's kind of forced to be paired with j because it's on the edge, but by introducing this new element I, we're kind of freeing it up to have the option of pairing with the element before it. And then we can kind of do something similar one more time, where we use this green subproblem that I've kind of drawn a rectangle type thing around. And again, that's kind of like we're freeing up this last element here that was forced before to go with the last element to now connect to this new element that we're introducing I. And so then all we have to do is we have to just minimize over these three possibilities, the three subproblems that will have their own cost associated with them, and then we just add in the distance of the this new edge that we add in, the new ending, which is always going to be the same. For actually implementing the algorithm, all you have to do is create a distance matrix, and essentially what you do is each cell in the matrix is going to represent the distance between the subproblem for the I and jth index that you're at. So for example, this value 3 right here is going to be the distance between the sequence 3, 4, 4, 2 and 2, 4. And all you have to do is, like in the previous slide, you just look at the minimum from above to the top left and to the left, and that minimum value is 1, and then you add that to the distance between the end values, which are 2 and 4. So you end up adding 2 to 1, and that's where this value 3 comes from. And you basically just loop through the whole matrix, building it up, and then you return out the bottom right value. And I guess the only other thing you have to account for is the base cases. So we start with this 0th index as the kind of represents like an empty sequence, and we define the distance between two empty sequences to be 0, and the distance between an empty sequence and any other sequence to be infinity. And that's really just done because it's kind of like an invalid comparison. We want to be minimizing over these values. You could do it another way. You could just fill in the first row and column manually, and then go from there. But this is a pretty common way that you'll see it done. And yeah, once you have that, that gives you the distance. And then if you need the alignment, all you have to do is start at the bottom right or top left, and then just follow the minimum values from above and to the left and to the top left, and that will give you the alignment. And basically it's just whatever cell you land at, that's the pairing that comes up. So you can see here that we come across these two 4 values, 4 and 4, and that's where these lines come from. And yeah, I guess that's how the dynamic time warping algorithm works.